function 3, 3 and 3, 5 at the same time. For this function, we came up with the domain. We came up with the terminal behavior, and we found out that there are no vertical asymptotes, but there is a horizontal asymptote, which is the x-axis. And so these two limits are telling you that as x gets bigger and bigger, the gap between the graph of the function and the x-axis is going to 0. Here, as x gets larger and larger in the negative direction, the gap between the graph of the function and the x-axis is becoming 0, right? That's what these two limits are telling you. And then we found out the intercepts, and we found that there is exactly one intercept. After that, we looked at the fourth step, which is find where the function is increasing and decreasing. We found out the derivative. We found out the critical points, and we came up with the sine graph for the derivative. We found out where the function is decreasing, increasing, and that told us by using the first derivative test, we can say that. So remember, we were in question number 4, we were trying to find the critical points of the function and classify them by using the first derivative test, and we did that, right? We used the first derivative test to say that we have a local mean at -2 and a local max at +2. What I want to do is do the same problem by applying the second derivative test. So here's the question that we want to answer now. Find. Okay, now let me just say. Redo step or redo part 4. Redo part 4 using second derivative test. So remember, in part 4, the question was find the critical points, classify them by using the first derivative test. Same question, except that we want to use the second derivative test now. So in order to do that, I need what? I need the second derivative function. So what's the second derivative function? Let's recall what was the first derivative. The first derivative was 4 minus x squared divided by x squared plus 4 squared, right? So let's recall. Let's recall that the first derivative was x squared minus 4 over x squared plus 4 squared, right? Is that the one? And then I need to find the second derivative of that. And of course we will be applying the quotient rule. So what am I going to get in the denominator? In the denominator I would be getting what? X squared plus 4 to the 4. I have to square the denominator, and then I will have the denominator multiplied by the derivative of the numerator minus the numerator multiplied by the derivative of the denominator. What's the derivative of the denominator? Anybody? 2x squared plus 4 times 2x. Okay, so that's the second derivative that we should be obtaining, and how do I simplify this? How would you simplify this? Would you multiply out everything and simplify? Yeah.
I have written down yesterday that the numerator of the
derivative
was 4 minus x.
The derivative of the numerator of the derivative
Yeah.
is 4 minus x squared. Negative x squared plus 4, which means I'll have negative x squared plus, let me just erase that, negative x squared plus 4, which means I'll get a negative 2 here, right? Yeah, that should be a negative 2 there. You guys see that? Negative 2 there. Okay, and negative 2x, okay? Okay, so that does it. And now how would you simplify this? Would you multiply out everything? You could, but the better thing to do would be try to factor out what you can. So notice we can factor out a 2x. We can also factor out x squared plus 4. And if I do that, what should I obtain inside the brackets? Do I get negative x squared plus 4 from the first term? What are you going to do? You're going to divide the first term in the numerator by what you're factoring out. So if I divide the numerator, the term x squared plus 4 squared times negative 2x, if I divide that by 2x x squared plus 4, what do I get? I'll be getting negative x squared plus 4, right? And then here I will have negative x squared plus 4 and multiplied by 2 left, right? You agree with that? Because 2x x squared plus 4, this whole thing here is being factored out. Okay, so what am I getting then? The denominator is still x squared plus 4 to the 4. And now notice that the denominator x squared plus 4 to the 4 and the x squared plus 4 in the numerator, we can combine them, and I would write x squared plus 4 to the what? This should be x squared plus 4 to the what? 3, right? 4 minus 1. And then within the brackets, what do I have? Well, I just multiply out and see what I have. I have 2x squared minus x squared, so that's x squared. I have a minus 4 and a minus 8, which would be a minus 12. Would you agree with that? Everybody's okay? So that's it. That's the second derivative, and it is in simplified form. Remember, I want to use the second derivative test to classify the critical points. So second derivative test. What are the critical points? We already found the critical points before, right? The critical points were at... You guys remember where the critical points were? Were they negative 2 and positive 2? Say it again? Yeah, so we had the critical points at negative 2 and positive 2. So how would I apply? So I need to know whether I have a local max or a local mean at each one of them. The second derivative test says, well, apply the second derivative at negative 2 and apply the second derivative at positive 2. And if I apply the second derivative at negative 2, what do I get? Well, let's look at the second derivative here. So you're going to plug in negative 2 for x. So plug in negative 2 for x here, negative 2 for x here. What am I getting? Positive or negative? You plug in negative 2, this is negative, negative 2, this is negative, right? Negative, negative, positive. Denominator is positive. Altogether it's positive, right? So I get that this is positive. So the second derivative says that f of negative 2 is what? Local max or local mean? Second derivative at the critical point negative 2 is positive, means the concave up. The function is concave up there. So you have a local what? You have a local mean there. And the second derivative at 2, if you go back again to the second derivative formula, I'm now going to plug in 2. So 2x would be positive. 2 squared minus 12 would be negative. So positive, negative divided by positive, which would be negative. Which implies that f of 2 is, well, if the second derivative at 2 is negative, it means that the function is concave down there. And if it is concave down there, I have a local max there. Does that match what I obtained from the first derivative test? You remember what we obtained from the first derivative test? Local mean at negative 2, local max at 2, and that's the same thing that I got by using the second derivative test. Is everybody okay? Any questions? You guys are okay with that? So in part 4, we found the critical points and we classified them as local max or local mean, once by using the first derivative test and once by using the second derivative test. Now I'm done with 3.1. That's what from the question from 3.1 is. I want to now continue with this problem, but now my goal is to draw the graph of that function. So now I'm going to say I have this step 5. In step 4 or part 4, I already determined where the function is increasing and decreasing. Now I'm going to say let's continue that and find out where the function is concave up and down. So concavity. So determine concavity of the function. So how do I determine the concavity of the function? Well, I need the second derivative, and we already have that. The second derivative is 2x times x squared minus 12 divided by x squared plus 4 to the 3. And in order to come up with the concavity, what do we need? What do we need? We need to come up with the values of x where the function is what? We need to, now this is part, in order to compute the, in order to determine the concavity, the first step, find the second derivative. The second step is what? Solve, right? Solve f double prime of x is 0, or f double prime of x does not exist. Well, is it clear that the second derivative is defined everywhere? If you look at the formula for the second derivative, the denominator is okay for any x, right? Because the denominator doesn't vanish anywhere, right? X squared plus 4 is at least 4. So we know that we don't get any solution from this. So how about the second derivative equals to 0? The second derivative equals to 0 would mean that the numerator, which is this, that numerator would have to be 0, which would mean that x is 0 or x squared minus 12 is 0, right? Which then means that x is 0 or x is what? Plus or minus root of 12, right? What is root of 12? 4 times 3, so 2 radical 3, right? And if you have a calculator, can you tell me what is that approximately? Well, I should say plus or minus. What is that approximately? 2 times radical 3. So the third step would be make a sign graph for the second derivative. And the second derivative, what are the critical points I have at negative 2 root 3, 0, positive 2 root 3. Is the second derivative positive or negative on the left side of negative 2 root 3? What is negative 2 root 3 about? Plus or minus 3.4? We'll just say 3.5. Okay, so I want to know the sign of the second derivative on the left side of negative 2 root 3, right? How would I calculate that? Well, look at the second derivative. And the second derivative is right here. What should I plug in to decide that? I should be plugging in negative 4, right? If I plug in negative 4, I get 2x would be negative. Plug in negative 4, x squared minus 12 is what? Negative or positive? Positive. So negative, positive divided by positive, I get negative. So negative here. Between negative 2 root 3 and 0, we can plug in negative 1, right? If I plug in negative 1, is the second derivative positive or negative? Plug in negative 1, you get negative divided by positive, right? So that will be positive. Look at the second derivative formula, you'll see that. If you plug in 1, 2 times 1 and 1 squared minus 12. So positive, negative, positive, which would be negative. And finally here, you plug in 4, you'll see that you get positive. So the function f, concave down here, concave up here, concave down here, concave up here. Are we okay with that? Is everybody okay with that? So we know exactly where the function is concave up and concave down. And so this was step number 5. And step number 6, we want to know in step number 6, we want to compute some points on the graph, okay? Because we want to draw the graph of the function. So what points do I need to plot? Well, I need to plot the intercepts. So let's recall what are the intercepts. I think we found only one intercept, right? Am I correct? Look back into your notes. I think we got only one intercept. Now, in step number 4, we got two critical points, right? One of them was negative 2, and the other one was positive 2, right? We need to know the point corresponding to those on the graph. So that means I need the y value for those critical points, which means I need to evaluate the function at negative 2 and positive 2. Okay, can someone tell me what are those values? What is f of negative 2 and what is f of 2? Do you have a calculator? F of negative 2 would be negative 2 divided by 8, which would be negative 1/4. So this is easy to know. And this would be positive 1/4. If you look at the original function, we are plugging in the original function, which was x divided by x squared plus 4, right? Is everybody okay with that? Now, we also found some critical points for the second derivative, right? When we looked at the concavity, we found the points 0. F of 0 would be 0 because we know 0, 0 is the intercept. And then we also found two other points there, 2 root 3, and we also had that f of negative 2 root 3. And I of course need the calculator to come up with that. So can someone tell me what is f of 2 root 3? What is f of 2 root 3? This would be 2 root 3 divided by 4 times 3 divided by 16, I think. And this would be negative 2 root 3 over 16. So we need to know the approximate values of this, okay? So these are approximately what? What are these approximately from your calculator? What's that? Okay, 0.21, and this will be just the negative of that. Negative of 0.21, okay? Okay, so how many points do I have here? The points that I have right now are the points 0, 0. I have the point negative 2, negative 1/4. I have the point positive 2, 1/4. I have the point 2 root 3 was about what again? 3.5, about 3.5, let's say 3.5 and 0.21. And we also have negative 3.5 and negative 0.21. So we have to plot all these 5 points before we sketch the graph of the function. Is everybody okay with that? Okay, let's try to sketch the graph now. So this would be step number what? I think this would be step number 7. To sketch the graph, we need the x-axis. We need the y-axis. Okay, let's plot the points. I'm going to use maybe magenta for the points. So I have a point at 0, 0. That's pretty easy to do. And I have to pick some scale, I guess. So let's see. We are not going to use the same scale for the x and y axis so that visually you can see what's going on. So let's say I have 1 here and 2 here, 3 here, 4 here. So 3.5 would be about there. So negative 1, negative 2, negative 3, negative 4 about right here. What point do I get for negative 2? I get about 0.25, right? So let's say 0.25 is right here, okay? My scale for y-axis is different. 0.25 is there. At 2, the value is 0.25 positive, so that's the point I get. At 3.5, which is right here, at 3.5, which is here, what's the value? 0.21, right? So 0.21 is pretty close to 0.25. So this is 0.25, so let's say 0.21 is right there. And at negative, so this is negative 3.5. And we would get something like here, let's say, 0.21. Is everybody okay? So this is 3.5. Here, this is 2 here. This is negative 2 here. Okay, once we plotted those points, now we are going to use the information about increasing, decreasing, concave, up and down. Okay, someone tell me how the graph looks like up until negative 3.5. Until negative, remember what's going on at negative infinity. At negative infinity, the value of the function is getting closer and closer to 0, which means the graph is getting closer and closer to the x-axis. At negative infinity, the graph is getting closer and closer to the x-axis because I have a horizontal asymptote there, right? Now, negative infinity up till negative 3.5. What's going on? Is it decreasing? Is the function decreasing? Go back to your step 5 where we decided where the function is increasing and decreasing, right? Look at that and tell me, until negative 3.5, is the function decreasing or increasing? Decreasing. Is it concave up or down? Concave down. So I know that it is decreasing and concave down up until this point, right? And at negative infinity, the graph is getting closer and closer to the x-axis, right? So that's how it should look like. Okay, what's happening between negative 3.5 and negative 2? Still decreasing? Concave up or down? Concave up now, right? So it is going to be concave up now. And then from negative 2 to 0, it's still concave up, but now increasing, right? So now it's increasing and concave up. And between 0 and 2, it is concave down, you'll see. It is still increasing, so concave down would mean like this, right? And then between 2 and 3.5, it is still concave down, I think. Is it correct? And it is decreasing after that. And after 3.5, it is decreasing, but concave up, right? So it means like that. And I know that the graph is getting closer and closer to the x-axis after that, right? So that's how it looks like. What are the inflection points? What are the inflection points? Let me call them IP. Inflection point at this point, because concave down and then up. And it is concave up until where? 0. So at 0, I also have an inflection point because the concavity changes there. And the concavity changes after that where? Right there. Is everybody okay? So what's going on with, I have concave down up until negative 3.5, and then concave up until 0, and from 0 to here it's concave down again, and then concave up at the end, concave up. Is everybody okay? That's how it looks like. Okay. I won't do any more examples on graphing. As you can see, it takes a long time to go through that. So I will not do that anymore. But if you have questions, you can ask me and come by my office, email me, and I can answer that. But remember, these videos are in Moodle, so if you are not sure at any point when you do your homework tonight, if you get stuck, look at these videos, see what steps I'm following. Also, the video that I sent you, that has another example on graphing. So now you have seen 3 examples of graphing if you have seen that video as well. Okay. On Monday, I'll be coming with some more exercises on graphing, but I'll be asking you to do them. And you can ask me questions. So basically, I'll give you some functions. I'll give you sort of the answers for each step, but I want you to verify from your work that those are the right answers, and then draw the graph. Okay, so 3.5, I am officially done with it. And what I want to do next is do one problem from 3.7, and that problem is the following. 3.7, that's a section on optimization problems. And so let's do one exercise from there. One example is the following. A farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field, that borders a river, what are the dimensions of the field that has the largest area. Okay, so that's the question. What problems? Always you just have to read and read and read a couple of times to make sure you understand what is being asked. Make some diagram in order to understand the problem. So in this case I will make a diagram which is let's say on this side you have a river, and the farmer is trying to make a fence off a rectangular field like this. And so let's say the dimensions of the field are X and Y. Okay. On the side, so he doesn't need to fence off the side that is facing the river. Okay. So, and the area, enclosed area, let's denote that by A. So you need to denote the quantity that you are trying to maximize or minimize. Okay. So so in all these problems, you're trying to optimize certain quantity. Okay. Label that the quantity that you're trying to optimize, and label the quantities that you're trying to find. You're trying to find the dimensions, right? So label the dimensions. One of them we are labeling by X, the other one we are labeling by Y. So what are we trying to do? Maximize the area. Okay. Now, so the question is, he has only 2,400 feet of fencing available, and the question is, so let's say he's allowed to make his field any way he wants to. Okay, it has to be a rectangular field, but he can use as much of the land as he wants to. Okay, no restriction on it. The only restriction is that he has 2,400 feet of fencing. Now, how should he pick the dimensions so that the enclosed area is as large as possible. Am I making sense? That's the question. So he wants to maximize the enclosed area given that condition. So let's think about the problem a little bit. So again, what are we trying to maximize? We are trying to maximize area. And what is the area? Area is x times y, right? Length times the width. And then, but of course, if he is allowed to pick x and y to be as big as he wants to, then there is no limit, right? He can make the area as big as he wants to. However, there is a restriction, right? What's the restriction? Subject to the restriction that he has only 2,400 feet of fencing. In terms of x and y, what does it mean? Yeah, it means that the parameter that he can pick for the three sides is got to be 2,400. So the restriction is that 2x plus y needs to be 2,400 feet, right? So maximize the area subject to the restriction that the parameter of the three sides has to be 2,400. Now the problem here is the problem now is the function that I'm trying to maximize. So I'm trying to find the maximum value of the function a given the restriction that 2x plus y is that. But the problem is I could solve this problem the way it is stated now if I was in Calc 3. Because in Calc 3 I can deal with functions of two variables. The area is a function of two variables here. I can't deal with it at this point. So how can I deal with it? Well, I have to express it in terms of one variable. So can I do that? Well, notice that I can express a as I can rewrite my restriction equation, my constraint. I call that the constraint equation. I can rewrite that as y equals to what? 2,400 minus 2x, right? So now in the area formula I can replace y by 2,400 minus 2x, and that would tell me that a is what? 2,400 minus, not 2,400, 2,400 times x minus 2x squared. So that's my area function, and I want to find the maximum value of this function. But if I ask you to find the maximum value of this function, I have to tell you on what domain. So I need to know what are the possible values of x now. What are the possible values of x? Well, let's check. That's the reality check that we have to do. I cannot pick x to be whatever I want to. Am I making sense? So let's see what I can make x to be, right? X has to be non-negative, right? So I know that x has to be non-negative, no question about it. It's the length. Now, but can I pick x to be any large positive number? Well, the answer is maybe not. Why? Because notice that y has to be non-negative as well, right? However, what is y? Y is this quantity. So I need 2,400 minus 2x to be non-negative as well. But that tells me that 2,400 is larger than 2x, which means I need 2x to be less than 2,400, which means I need x to be what? Less than 1,200. And now I can say the following, that I want to say that maximize A equals to 2400 minus 2x squared, where x is between 0 and 1200. Now this is just a pure calculus problem, right? The hard part is to come up with the function of one variable to maximize or minimize, and coming up with the right domain on which you want to maximize or minimize. Once you have that, it's just the same old calculus. How do I find the maximum value of this function on that domain? Well, my function, area function here, is a continuous function on a closed bounded domain. Remember, I gave you a handout on finding the absolute maximum of a function on a given closed interval, right? How do you do it? Well, you find the critical points. So what's the critical point here? The critical point here is what? Yeah. Yeah, this was 2400x. Thank you. The area would be 2400 minus 4x, and so what would be the the derivative is defined everywhere. So what are the critical points? Well, I have to solve what? I have to solve 2400 minus 4x equals to 0, and then x would be what? So I get only one critical point. Now, extreme value, remember, if I have a continuous function on a closed bounded interval, then the maximum value occurs at the critical point or at the end points, right? Or at the end points. So all I have to do is figure out the value of the function at the end point 0, at the end point 1200, and at the critical point 600. What are the values of the area? Well, at the end point 0, if x is 0, then the area would be what? 0. If x is 1200, note that y value would be what? Y value would be 0, and then area is 0 again. So I know that whatever that is, that's going to be my maximum area. So the maximum area occurs when x is 600. When x is 600, what is y? What is y? 1200. Right? Because remember, y is 2400 minus 2x. And so these are the dimensions that needs to be picked to make sure that the enclosed area is largest possible. Okay? All right, we'll have to do more examples next time.